Hello, welcome to this other video. Today I will be talking about isospin and ladder operators and the Krebs-Gordon coefficients table and how to understand how to use them. Okay, let's first start with isospin and what isospin is and what is useful for. So each particles will have different projections. So for example, pions, they have three different projections: pion plus, pion 0 and pion minus. The projection with the highest, with the positive charge, will also have the highest projection out of all of the projections, and also the one with minus charge will have the least projection, so in this case -1. So they're very easy to differentiate and remember the projections. Also, the strong force is does not really care about color. So in this example for the nucleon, we have a proton and a neutron, and that's because their masses are very similar and therefore are not differentiated. So we call this particle nucleon. So the highest projection is a proton and the lowest projection is a neutron, respectively, with isospin projection +0.5 and -0.5. Okay, now that we have defined kind of what isospin is, isospin is useful to calculate the probabilities of decays of different particles. And we can use something called the isospin ladder operator to find these probabilities and move between projections of particles. For instance, if we apply the minus operator on pi minus, we will get to pi 0. And if we apply it again, we will go to pion minus, and so on. For more complex systems, such as, for instance, delta particle decays into a nucleon and a pion, which are the two particles over here. This is a more complex system. So for this, we will have, so for the plus operator, so if we want to go up in projections, we will apply the plus ladder operator on the first particle, so in this case it's the nucleon, times the second particle, so in this case it's the pion, and then plus the first particle, so nucleon, times the ladder operator plus applied onto the second particle B. And on the other side, we can do the if you want to go down in projection on a system, you can do the same thing, but just you need to apply a different ladder operator, so the minus operator. So this is a little bit easier to see on an example, so let's now do an example. Let's move on. So we have now this example, which is delta particle decays into a nucleon and a pion, and we want to find out what the different projections will decay into. So the delta particle has 4 different projections, and it's delta plus, delta plus, delta 0 and delta minus, and we need to find out the different projections. So the different possibilities, how I like to start the question is, you need to remember that the highest projections and the lowest projections only have one possibility, only one combination, and that is, so for plus, we need to conserve charge. So the only way that you can get plus is if you combine the proton with the pion plus, because they conserve charge, because charge of a proton is +1 and charge of a pion plus is +1 as well. And then we go on to the delta minus. So this one we'll have, since we need to conserve charge, the only way that we can do this is to have a neutron and a pion minus, again because they conserve charge both ways. Now we need to fill in the gaps. So we can have different combination for these ones. So to get delta plus, and this time we have to conserve charge only for +1. So we can either get proton combined with a pion 0, plus we can either get a neutron and a pion plus. Then we need to do the delta 0, and delta 0 can either be the neutron with the pion 0, or it could be the proton with the pion minus, because the charge is again has to be conserved. I like to start on the highest projection, so we're going to start from delta plus plus, and we're going to move down in order to find delta plus, and then we're going to go from delta minus here to find delta 0, and we're going to apply the plus ladder operator. So let's start. Here are a few rules that I put up to remember. So this is the equation, the general equation for T minus over here, and T plus is very similar, just the other way around. And then I'm going to write down the other important equation. Ladder operator for T minus will be square root of isospin plus 1 minus isospin z projection times isospin z plus 1. And then ladder operator plus, sorry, this is the plus operator, and the minus operator will be isospin plus 1, and then minus z projection minus 1, and this is the minus ladder operator. Okay, so let's apply the minus ladder operator onto the delta plus plus. So delta plus plus, and we're going to apply the T minus operator, and we will write down 3 over 2 plus 1 minus 3 over 2 minus 1 all square root, and that will give us square root of 3. Okay, and then delta plus. So this is the probability of the delta plus plus going into delta plus. So now we need to apply this equation onto our proton and the pion plus. So we're gonna firstly apply the ladder operator minus on the proton, which will be root of 1, and this will become n pion plus. And the reason that we know that it's n pion plus comes from this equation, because now that we have applied the T ladder operator minus onto the first particle, which for us again it's the proton, you will end up with timesing it by the B particle, and we know that when we finish up, the B particle will be our pion plus, and the only one that has pion plus in this equation is the first term, so we know that this is the right probability for that one, so it's the neutron and pion plus. And then we need to calculate the ladder operator on pion plus, and that gives us root of 2 proton pion 0, again for the same reason of the same rule. So now we put everything together and we get root of 3 delta plus is equal to 1 n pi plus plus root 2 proton pion 0. And then we divide everything by root 3 to find the correct probabilities. And we find that the probabilities for a delta plus to decay is 1 over 3 for the n pion plus root 2 over 3 proton pion 0. So this is our first probability. And to cross-check it, we will use the Krebs-Gordon coefficient, but I will do it in another video, otherwise this will be a bit too long. And then now we will do another projection, so another example going from delta minus to delta 0. So we need to apply the same process, but this time we're going to use the plus operator. So we're going to apply the plus operator onto delta minus in order to get the probability for delta 0. And that will be 3 over 2 plus 1 minus 3 over 2 minus 3 over 2 plus 1 all square rooted, and that gives us root of 3. Be careful with the signs because otherwise you will get it wrong, and you need to be careful about the signs. So now we're going to apply again the same rule, this time for the complex system. The plus operator, because we're going up from projection, and we're going to apply it to the neutron pion minus. I'm going to extend the equation so it's a little bit easier to understand. So we're going to do ladder operator plus on pion minus n plus t plus n pion 0. So now let's do the calculation. T plus pion 0, and then we will get root of 2. I'm not going to go through the calculations, but do go through them and try and prove the maths right. So then the ladder operation plus on the neutron will be just root of 1. So remember, we calculated the ladder operator on minus pion minus, so we know that this is the projection with the neutron, and the one with the neutron on the delta 0 is the one that has neutron and pion 0. So we can write that down, and then this will be the other one, so it's the proton and pion minus the projection. So now we write everything down, and that will be that it's the root 3 delta minus is equal to root 2 n pion 0 plus root 1 proton pion minus. We divide everything by root 3 again, and we get that the probability for the delta minus reaction to decay in these two particles is the one written right now. Okay, so now that we have successfully calculated and proven this decay probabilities, you can see how these ladder operators are very useful in order to find the probabilities of a decay. So I hope that you found this video useful, and in the next video, I'm gonna link it down below. We're gonna see how these probabilities, how you can cross-check these with a very useful table, which is this one down here, the Krebs-Gordon coefficient table, and we're going to prove it in the next one.